Let's do a moderately quick example of arc length, not as bad as it could be. How about the arc length of this function x to the 3 halves from x equals 0 to x equals 7? Good idea to graph it first. What do you think it'll look like when we graph it? Well, it's a power over 1, so it's probably going to look kind of curved up like a parabola. Not quite as much as a parabola, because this is x to the 1.5 instead of x to the 2. So we'll just draw it kind of like that. Goes out here to 7 we're stopping at. What should we do before we do any fancy integral stuff? How about upper bound, lower bound, and guess on the arc length? So what can we do to get an upper bound or a lower bound or guess? Well, a quick lower bound would be 0, right? A better lower bound. Can you think of a way to get a better lower bound on the arc length directly without having to think about all that integral stuff? You could say, draw a straight line from the start to the end. A straight line is the shortest distance between 2 points, right? So that's not a bad idea. How about an upper bound? Well, it's actually hard to get a good upper bound generally. If it has this shape, you might say, well, going over, straight over, and then straight up would be reasonable, I think. Something like that. So we're going this way and then that way. You agree that that's longer than the curved path in between there. So here's a puzzle for you. Can you think of a curve where going straight over and straight up would not give an upper bound on the arc length? It's kind of fun. All right, so now that we've got some ideas for upper bounds and lower bounds at least, let's write the arc length formula. Integral a to b square root of 1 plus f prime of x squared dx. What is f prime? We're going to need to know that, right? So f of x here is x to the 3 halves. F prime is 3 halves x to the 1 half. While we're doing it, why don't we do f prime squared? That would be 3 halves squared x to the 1 half squared, which would be 9/4 times just plain x. That's kind of handy that the square root, that the 1 half power cancels the 2. So we've got integral from 0 to 7, our start to end point, of 1 plus 9/4 x dx. And how are we going to solve this one? Take a sec to think about it. Well, we've got something inside a square root, so if we've got something inside, then maybe u substitution, right? We could also write this as 0 to 7, 1 plus 9/4 x, sorry, not the square root there, but writing this to the 1 half power. So we could use u equals 1 plus 9/4 x, du equals 9/4 dx, or 4/9 du equals dx. And now there'd be 2 ways to solve it. We could translate all the start and end point to u values. So let's try that over on this side of the paper. I'll make a little table of x and u. When x is 0, u is 0 times 9/4 plus 1, so you get 1. When x is 7, you get 7 times 9/4 plus 1, whatever lovely number that is. And then we'll rewrite the integral u equals 1 to u equals, let's just call that b, of u to the 1/2 times 4/9 du, and take the antiderivative. What's the antiderivative of u to the 1/2? It's u to the 3/2, 1 over 3/2 times 4/9 from u equals 1 to u equals b. We can pull all these constants out front. 1 over 3/2 times 4/9 times b to the 3/2 minus 1 to the 3/2. And let Desmos do all the plugging in algebra for us. Or we could do it all as indefinite and then plug in our 0 and our 7 later. So we can just say this is the integral u to the 1/2 times 4/9 du. And that is 1 over 3/2 u to the 3/2 times 4/9. Now substitute back in, and we get 1 over 3/2 4/9 times whatever u was, 1 plus 9/4 x to the 3/2. And so let me put the kind of indefinite stuff in its own little box here, and then all of that is from x equals 0 to x equals 7. So since I don't feel like doing this arithmetic, and I'm pretty sure you don't either, let's go have it done in Desmos, just to check. All right, here we are. We've got our function. We've got our start and end points shown here. We could compute a lower bound, which would be the square root of the difference of the x's, right? 7 minus 0 squared plus f of 7 minus f of 0 squared. So that's our lower bound. That would be the straight line distance from one to the other. So what did we say our integral was? Let's see. Well, we could just type the integral directly. We could type from 0 to 7 square root of 1 plus, and then we could actually get Desmos to do the derivative for us. And did we get something slightly above our lower bound, but not quite the same? Yep, so that's pretty good. But that's not showing that we know how to do the calculus by hand. We could say, let's see, what do we have? Our antiderivative, so let's call that f of x, was 1 over 3/2, 4/9, 1 plus 9/4 x to the 3/2. Now actually I don't really care what that antiderivative looks like. I don't really care what this integrand looks like. I'm trying to think of it just in kind of actual curve length. So I'm going to turn that graph off. And now if I say big F of 7 minus big F of 0, then we get the same answer that Desmos gets when it does little tiny difference quotients for the derivatives, squares them, and then adds it all up using, squares them, adds them in 1, takes the square root, and integrates using kind of a Riemann sum numerical integration approach. And we get the same answer down to a very good number of digits.